This is Physics 2212, Lab 5, Magnetic Molasses. As an introduction, here are some goals and results. So for our goals, we're collecting observation of data through a magnet falling through a tube of aluminum foil, and then we'll be simulating the falling of that magnet through the tube with a computational model using GlowScript. And then we'll be comparing the simulation with the real world results. And so for real world results, our average time was 1.183 seconds, and our computational time with the computational model was 1.13 seconds. And so the difference between those is 0.047 seconds. Some of the key concepts, i.e. formulas that we're using in this lab, are the Biot-Savart law, which you can see is right up here, and then we'll also be using Faraday's law, which is the one that explains how the magnet slows down through going through the tube. And then I forgot to explain the Biot-Savart law, but this is just the change of magnetic field. And then we have Newton's second law, which is force equals mass times acceleration. So for our observed model, like the real world experiment, the conditions are as follows. We have the aluminum foil tube length set at 0.305 meters, and then the width of the tube, like from inner radius to outer radius, is 0.02 meters, and then the inner radius of the tube is 0.03 meters. So our system in this experiment is the bar magnet, and the surroundings are the aluminum foil tube. And then for our procedure, we're just timing how long it takes for the magnet to fall through the tube, and then we're taking the average of all the trials. Here's some code for a computational model. As you can see here, we have some of the constants and the properties of the magnet. And so we have the magnet, the dipole moment, as like is the same from lab 3, and you can see that here. And then we made a function to calculate the magnetic field of the bar magnet right here, and then we made a function to calculate the flux. And so all these create things to measure the force on the magnet, and so then we put it all together and find the F net from the magnetic and the gravity forces. And so here for our next slide, we have the graph of the velocity versus time and of the computational model. As you can see, it speeds up pretty quickly, and then it actually slows down a little bit and has constant speed for a while, and then it speeds up again once it gets out of the tube. So here are results that I talked about from earlier. Our average time from the real world experiment is 1.183 seconds. Computational time is 1.136 seconds. The difference between the two is 0.04 seconds. And then some possible sources of error in the experimental time to result in the difference is that our timing method could be screwed up, the dropping method could be screwed up, the dipole moment of the magnet is an approximation, it's not constant. So, and the drag forces are not really accounted for. There could be friction from the magnet hitting the edges of the tube and air resistance. On to our what if questions. What if the resistivity of the conductor were reduced to as close to 0 as possible? So if the magnet had very little resistivity or little dipole moment, then it would slow the magnet's fall even more. And so, yeah. And then what if there were holes or slots cut into the tube? How would this affect the ring currents in your model? The current would decrease, so there wouldn't be as much area of the magnetic field, and so this would allow the magnet to fall faster, and that's it.